What's up, my dudes? So we want to. I'm going to start this over. I know we started this morning, but good thing for us to review. So, here's where we're at, right? We did a demonstration where we shot something horizontally at the same exact instant that we dropped something, right? And that was a really, really important demonstration, right? What it showed us, well, it's really summarized in this slide. If we drop something, right, just that word by itself tells you something, gives you the value of a given, right? It tells us that initial velocity is 0, right? So here's our object that we just dropped. And this thing, as we've done in free fall, which we started 2 or 3 weeks ago, right? This object that free falls, as time goes on, gets a little faster, goes a certain distance, gets a little faster, goes a little farther, gets a little faster, goes a little farther, and so on and so on. Okay? Now, the thing that we shoot horizontally, here's the big, big deal. And we came up with this as a group together. You were there. It means that the initial vertical component of its velocity is 0. The horizontal part of the initial velocity is not 0, right? It's shot with a horizontal velocity. And as you can see, that vector has absolutely 0 vertical part, right? Its vertical component is nothing. Now, if we look at the vertical part of this thing's motion, well, since these two objects have the same initial vertical velocity and they have the same acceleration vertically, they're going to fall the same distance if we say this is the same amount of time. All right, now, horizontally, what we know is that horizontal velocity stays constant. And one of us said that real well today, because there's no force horizontally, there's no side-to-side force, there's no reason this object should slow down or speed up horizontally, right? So horizontal speeds stay the same, and this is, we're supposed to be able to understand that this vector represents the horizontal component of velocity, and this vector represents the vertical component of velocity, okay? So as time goes on, right, this object vertically is exactly the same as something that's dropped. Horizontally, it just happens to keep moving sideways at a constant speed the whole time it drops. All right, so here's what we have. We have a few things we can point out. One is that this object has what we call an overall horizontal displacement. It goes that far. These both have an overall vertical displacement, which is the same exact thing for each. I guess we're saying it stops here. Oops. That it goes, and that's the end of its vertical motion. Okay? So, yeah, those are what we call dy, vertical displacement, and dx, horizontal displacement. Right? Other things to notice here is, you should notice that these, what do I want to call these? These little incremental horizontal displacements all stay the same size, right? We should notice that, and we should be able to explain that because the horizontal velocity stays the same speed. So in the same amount of time, that distance traveled is always going to be the same thing. All right? Other things to notice, well, if we look at any instant at how fast this object is moving, the purple object, we can say that its velocity is actually that. That's its actual velocity, right? Not the horizontal part, not the vertical part, it's the whole thing. And I hope you can notice that V there is the resultant of Vx and Vy. If we add Vy over here, tip to tail with Vx, we get the whole vector V. All right, and notice this velocity vector, the actual velocity that the object has, keeps getting bigger and keeps changing direction, right? And hopefully we can see that that's why this thing moves in really this parabolic path. All right, that path is called a parabola. All right? All right, so big deal, right? These things have same time in the air. So really, this is just asking you that question again. Which would take longer to hit the ground? A bullet that you shoot horizontally or a bullet that you drop from the same height? I want you to answer that for tomorrow and explain why. Yeah, we've kind of already done this a couple of times. But write me an answer and tell me why. Okay? We'll check that tomorrow. Now, let's go to some equations. All right? Here's stuff that we know already. We also have that V average is D times T1, but we're going to kind of stick with these three for right now. All right? Well, here's the deal. If we want to turn these into projectile equations, and a projectile is, well, what's the definition of a projectile? We should make sure we talk about that, right? A projectile is an object that moves in 2 dimensions. And what I mean is up and down and side to side. And I'll say under the influence of gravity only. All right, so it's something that's in the air, but gravity is the only thing that affects its motion. Okay, so that's things like cannonballs and bullets and I don't know, a football or a lacrosse ball, anything in a tennis ball. Although tennis balls you can get a lot of spin on, that can sort of change their motion. But not a plane, and not a rocket, because rockets have engines and planes have wings that make lift. All right, so we need things that are going to follow a path that looks like that parabolic sort of, thing that comes off the table like we did goes like that. So, planes don't necessarily follow that motion. Rockets don't always do that. So only things that follow nice parabolic paths where gravity is the only thing that affects their motion are what we consider projectiles. All right? So to come back here, folks, the definition of a projectile, that's something we need to be sure that we're okay with, right? Not everything that moves through the air is a projectile. Only things that, have those nice typical parabolic paths where gravity is the only thing affecting the motion. Now here's what we do. All right, we have these equations that work for things that accelerate and even work for things that don't accelerate. What we have to do, just like in our boat crossing the river example, we said, we really have to be careful about not mixing directions, right? So what we're going to do is come up with a set of equations for the horizontal direction and a set of equations for the vertical direction, right? And they're a little bit different because accelerations are different in each direction. Okay, in the vertical direction, projectiles, have a vertical acceleration that's g, just like free fall stuff. All right, but here's a real important point. The horizontal part of a projectile's motion has an acceleration of nothing, right? Remember, forces cause accelerations. There are no forces in the horizontal direction, therefore there's no acceleration. All right, so here's what we do, right? We take, we take this, we can start with this first one, and we get that V is VI plus AT. Well, I'll just write that. What we're going to do is dress it up a little and make sure that we're only ever talking about vertical stuff in this equation. All right? Oh, sorry. This should say F, right? So should this. So this should really be VFY. Come on. VFY. Right? Same equation from before, but we're just making sure that we only use vertical stuff. Same thing with this second one. We could say that VFY squared is VIY squared plus 2G dy. Third one, we can say that dy is VIYT plus 1/2 G t squared. All right? So, if you notice, they're not new equations at all. We're just changing notation a little bit to make sure we see that we never, or that we only use stuff in the vertical direction together in one equation. All right? Now, if you notice, don't write this down. Don't write this down. Don't write this down. If you did this, VFX is VIX plus 0 times t, right? AX is 0. Well, all that tells us is this, that the final velocity and initial velocity in the x direction are equal. Well, that's not much of an equation. It doesn't do anything for you. You can just say you know that. All right, so the first one doesn't do you any good. The second one doesn't do you any good either. You're going to end up with this. Don't write this down. VFX squared equals VIX squared plus 2 times 0 times dx. Well, that just makes this whole term drop out. And then we can take the square root of both sides and end up with that again. Again, that's not a valuable equation. But the last one is valuable. If we do this, d equals vxt plus 1/2 times 0 times t squared. Well, let's just get rid of this whole term if a is 0. Here's an equation that is of a lot of value. The only one you'll ever use in the horizontal direction. What happened to that AX thing? There it is. Okay, so all three of these you'll use in the vertical direction. And you could use this one too. dy is 1/2 VIY plus VFY times t. That's the dy, or d is V average times t. So all four of those you can use, just like we used before. In the horizontal direction, though, that's the only one you'll ever use, ever. Okay? Now, how come we use Vx instead of Vix or Vfx? Well, because it never changes, right? Since acceleration is 0, horizontal velocity is constant, there's no reason to talk about the initial or the final if it's all the same thing. Okay? Now, let's do a couple of problems. My boy Todd Squire, went to college together. Lives in Cape Cod. We call him Cape Cod Todd. Yeah. Actually, we never called him that before one of my wife's friends. Never mind. Cape Cod Todd spits his gum horizontally out of an open window. I don't know. Let's say it's 3 meters above the sidewalk. He spits it with an initial velocity of 5.78 meters per second. How far from the base of the building will the gum land? This is the classic question. The classic horizontally launched projectile question. All right, not a bad idea to start with a a diagram. Right? Here's a vector representing the horizontal velocity, and the object, the gum, is going to do something like this, where it has some what we call dx, and it has some what we call dy, vertical displacement. All right? I'm going to tell you, we never, ever, ever care about this. We never draw that vector. It does nothing for us at all. So don't bother. Okay? Here's one thing I just completely recommend. Every projectile problem ought to start with one of those. A little chart, a little table, where you can completely separate horizontal stuff and vertical stuff. All right? Horizontal stuff we know. Well, notice, again, it's spit horizontally out of the window. So that means that this speed, like we said, is a Vx, 5.78 meters per second. Let's see, the window is 3 meters above the sidewalk. You know what that is? Well, that's a dy. And I'll say this. dy is 3 meters downward. 3 meters downward. Let's see, what else do we know? The question doesn't say. There are no more numbers in that question. So here's where you have to be a physicist. You have to be smart about what do you know about projectiles. Well, for any projectile, it's under the influence of gravity. So there is gravitational acceleration downward, 9.81 meters per second per second. All right, that works all the time. And here's the real big one. We've said this a number of times now. This word, well, we haven't really said it like this, but when an object is shot horizontally, it means initially it's moving this way, which means that initially it's not moving up or down. You see the word horizontally, that's what it tells you. Okay, that is a must. You need to know that. It needs to come right out of your brain when you see the word horizontally. Initial velocity in the vertical direction is 0. Okay? Now, we're looking for how far from the base of the building the gum lands. If you look back to the last page, you'll see there's only one equation we ever use in the horizontal direction. It's that. We need to know t. We know Vx. We need to know t. Well, with this stuff, we have enough to find t. There is an equation that has those 4 things in it, and that equation is what we love about this is that VIY is 0, so this entire term is gone. And we get dy is 1/2 gt squared. Or if we solve for t, that would be t squared, so there's t. Right, since these are both positive, since they're both downward, I'm just going to call downward the positive direction. And that means that we can say this is 2 times 3 meters divided by 9.81 meters per second squared. And let's see, that looks like somewhere around 2 times 3 divided by 9.81 equals 0.78 seconds. Really, we'll call it 72 seconds since there's 3 sig figs everywhere. Okay, now, that amount of time that it falls, it also travels horizontally. Remember that thing, the big demo we did? Which one spends more time in the air, the object that's shot horizontally or the object that's dropped? Well, they spend the same amount of time in the air. So we can use this time that we found with the vertical information on both sides. Just like we did with our boat going across the river. The time it takes to go one direction is the time it takes to go in every direction. All right, so dx here is now 5.78 meters per second times 0.782 seconds. dx is 5.78. dx is 4.52 meters. Okay? Most important parts. Really this, right? The horizontal part and getting to here. All right? If you're going to do well on these problems, that part has to come out of your brain automatically. All right? There's a pattern with these questions. The pattern is whatever you're asked for. In this case, we were asked for dx. Well, we had to first use y stuff to find time. And then we had to bring that time back to the other side of the table to find dx. All right? There's a potential question where, and there was one on your homework, where we're trying to find dy. Well, if you're trying to find dy, you're going to have to use the x stuff. and then bring that value of time over into the y side of the table. Okay? Whether or not you recognize it, this is the exact way we solved that hit the target lab question. You used vertical displacement, you used vertical acceleration, you used this fact that VIY is 0, you found out how long the ball spends in the air. And since you measured Vx with that B-spy, you could then use that amount of time, plug it in here with the horizontal velocity, and you found your dx. So this is the exact method you went through to solve that hit the target lab question. Okay? Now this one is a little bit different. Okay? What we're looking for, this thing does this. You know, if we go back to that slide before, we said this case here, how fast is it going? Well, it's actually moving. That's not a great direction. It should be tangent to this path. So I'm going to try to do better. If it's doing this, good, better. And the object is here, it's actually moving in that direction right now. Okay, not up, sorry, it's not moving straight down, it's not moving horizontally. There are parts of its motion that are straight down and parts of its motion that are horizontal, but the question is, what is this plain old V final? All right, I'll leave that as a bonus. It is not a question you'd ever see on a Regents exam, but it's a good bonus kind of question. All right, we'll keep that same 3 meters if you want to try to solve this problem. Okay? Okay. So, your homework is that sheet of problems. And actually, this kind of problem is the last one on the sheet, right? It's that, it's that last problem. So that one's optional, but the 4 that are on there are your homework. Okay, folks? I will see you tomorrow.